Yeah, it's in January.
All right, hi everybody, and welcome to our final colloquium of the year. So it's my great pleasure. Can I please take it back to the?
Right.
Well, it's my great pleasure to introduce Professor Clifford Will, who's joining us from Florida, and we'll be talking about the Renaissance of general relativity.
Thank you. In the popular imagination, there's a kind of fairy tale version of the story of general relativity that goes something like this. In 1905, working as a lowly clerk in the patent office in Bern, Switzerland, Einstein discovered special relativity. 10 years later, after a lot of hard work, he discovered general relativity. 4 years after that, Eddington measured the deflection of light by the sun. General relativity was triumphant. Einstein became famous. And everybody lived happily ever after. Now, the real story of general relativity is a bit more complicated than that. For example, there was a tremendous skepticism, especially among US astronomers, about the validity of Eddington's measurements of the deflection of starlight. Also, despite what you may learn or have an impression of physics in the early part of the 20th century, physics in Europe and the United States in those days was completely dominated by experimentalists. And they had no interest in this fancy theorizing, which had the only effect of producing meaningless and unmeasurable perturbations of Newtonian gravity, which had worked for 200 years just fine. Thank you very much. In fact, these experimentalists controlled the societies, they controlled the awarding of prizes, and they had no interest in general relativity. And so over the beginning in the late 1920s, general relativity entered a steep decline, so that by the 1950s, it was in the backwaters of physics and astronomy, not considered to be a suitable subject for a real scientist to pursue. And so what I want to do in this talk is tell a bit of this story. This is going to be mostly history, as I see it. I'm not a formal historian of science, so, forgive me if that's possible. So I'll talk about this early triumph, but then the decline into the backwaters. But then there was the beginnings of a renaissance in the 1960s with new discoveries in astronomy like quasars and pulsars. And I happened to be at the right place at the right time in 1969 to catch this rising relativistic wave at Caltech. And so I'll talk about some of my own experiences, focusing mainly on testing general relativity and also gravitational waves during that early period. And then I'll conclude with just a discussion of one example of what I think makes general relativity an exciting and vibrant field, unlike the earliest days, and that's the synergy between theory and experiment, something we take for granted in all science, but was sorely lacking in the early days of general relativity. So, of course, the popular story of this expedition to measure the deflection during the eclipse of May 29, 1919, is it was all about Eddington. But in fact, there were two other very important players in this story. Astronomer Royal Sir Frank Dyson and Charles Davidson, one of the great astronomical instrument makers of the day. Now, Einstein finished general relativity in November 1915, but this was in the middle of World War I, and Germany was completely cut off from the rest of the world by embargoes, and there was no scientific communication between Germany and most of the world. However, Willem de Sitter in neutral Holland managed to get copies of Einstein's November 1915 papers and forwarded them on to his friend Arthur Eddington in England. Now, Eddington was both a great astronomer and an accomplished theorist, and immediately recognized the deep implications of this new theory. He wrote a big report on general relativity for the London Physical Society to kind of spread the word about this new theory. And he and Dyson began to plan for an expedition to the eclipse of May 1919 to measure this predicted deflection of starlight. Now, Eddington had another motivation for wanting to do this experiment. Eddington was a member of the Quaker faith and a conscientious objector. And he deeply felt that the concept of a British team of astronomers verifying the theory of a German would bring about world peace and reconciliation, and we'd all walk arm in arm singing Kumbaya. Now, of course, in our cynical age, we think of this as completely, idealistic and unrealistic, but he deeply felt this as an important aspect of what he wanted to do. And it later will generate a bit of criticism of him. And in fact, Eddington had a conscientious objector status, but in the closing months of World War I, this is just before the Great Battle of the Marne, the Ministry of War was so desperate for manpower that they threatened to revoke his status. But an appeal by Dyson then caused them to overturn that decision, and he was free to not serve. World War ended in November 11, and the teams set sail for the site of the eclipse, Sobral and Prangip. Now, there are actually two teams. They set out from Britain to the island of Madeira and then split up, one team going to Sobral, a city in northern Brazil, and the other team going to the island of Prangip, at that time a colony, part of the two-island colony of São Tomé and Príncipe, for both, of course, in the path of the total eclipse. Davidson and Crommelin went to Sobral and set up two telescopes there. Eddington and his colleague Colloquium went to Prangip and set up their site here. This is on what's called the Sunday Farm, which I'm told 100 years later, a bunch of us actually went there for a conference to celebrate the exact anniversary of the measurement. This farm produced about 70% of the world's chocolate back in the 18th century, mostly slave labor, of course. And this is on the site of the Jockey Club, just outside the town of Sobral. So they set up their telescopes. In Sobral, there were two telescopes, a 4-inch and a 13-inch. As is often the case, the weather was atrocious. There was cloudy weather during the eclipse. Apparently, the 13-inch telescope spontaneously changed its focal length, maybe due to heating. 4-inch telescope gave 7 plates with 7 stars each. The idea of the eclipse, of course, is when the moon is in front of the sun, you see stars around the sun. You take the photographs, and then you compare those with a photograph of the same star field when the sun is no longer in that part of the sky, and measure the deflections between the two photographs, exploiting the fact that stars that pass closer to the sun are deflected more than stars that are farther from the sun. And then so you can fit that deflection by comparing plates. So in fact, they waited until July 11 to take the comparison plates after the sun had moved away, and departed to return to England in July. Now, Prangip had just one telescope. There was rain all morning, and just as the eclipse started, the clouds sort of cleared, and he was only able to get 2 usable plates with 5 stars each. Now, for various logistical reasons, they couldn't wait around to make comparison plates, so they used plates that had been taken earlier in the year at the Oxford telescope. So those are the plates they compared. They left the island in June 12th and arrived in Liverpool on July 14th. Now, again, the idea of the impression in the fairy tale is it was all the Brits, but the Americans were eager to do this experiment as well. In particular, William Campbell of the Lick Observatory in California and his colleague Heber Curtis were anxious to beat the Brits to a test of Einstein's theory. And they used plates from earlier eclipses, one in 1900 near Augusta, Georgia, and one in 1918 from Goldendale, Washington. In these days, astronomers took photographs during solar eclipses, partly to study the solar corona and solar photosphere, but also in the ongoing search for a possible planet between Mercury and the sun. We already had a name, Vulcan, as proposed in the 19th century. This was in order to try to resolve the ongoing discrepancy in Mercury's perihelion. Of course, we all know Einstein solved that problem with general relativity, but in the early days, this was an important goal of these kinds of measurements. So these plates existed. The problem was the images were poor, and they found no unambiguous evidence of the Einstein deflection. In fact, Campbell traveled to the summer 1919 meeting of the Royal Astronomical Society to report his negative finding on the eclipse, on the deflection. Ironically, at that meeting, Frank Dyson reported that he had just received a telegram from Eddington, sent from Prangip just before Eddington's departure, saying that Eddington, thought he would be able to report a positive result once he returned and did the full analysis.
They developed the plates.
I'm sorry?
They developed the plates on the site.
Yeah, apparently, yeah. Or enough that he could, yeah. And I presume they took the comparison plates with them so they could do some crude measurements just to see. So at the end of the day, Sobral obtained a result. If you extrapolate the deflection to the limb of the sun, you get 1.75 arc seconds. So they got this in agreement with the GR prediction, and the Principe result, this was from the 4-inch, of course. Principe result was also consistent with somewhat larger uncertainty because they only really had 2 usable plates. Now, in the 1980s, some historians of physics started to criticize Eddington's results, arguing, first of all, there was flimsy data. They wondered why they didn't use the 13-inch plate. Was it this, or was it because the 13-inch results disagreed with general relativity? Some accused Eddington of possibly unconscious or maybe even conscious bias because he was so enamored of general relativity. He got the result he wanted. Now, ironically, about the same time, a group at the Oxford Observatory took it upon themselves on the occasion of the centenary of Einstein's birth to reanalyze the plates from the Sobral expedition. The Principe plates apparently had been lost or destroyed at Cambridge, but the Oxford plates were there. They did a reanalysis with modern measuring tools and got results consistent with the earlier ones, almost the same as the early measurements. They even looked at the 13-inch plates and got a result in agreement with general relativity, but with larger error bars reflecting the added uncertainty due to this apparent change in focal length. So our friend and colleague Daniel Kennefic, both a relativist and a historian, has done a deep dive into this whole episode and concluded on balance that Eddington and the teams did the best they did with the data they had. There's no evidence of bias or conscious or otherwise in what they did. Now, Eddington was no stranger to self-promotion and publicity, so when he reported the final results at the November meeting of these societies, he arranged to have the press present and the whole hoopla, and the scene was aptly described by mathematician Alfred North Whitehead. The whole atmosphere was exactly that of a Greek drama. In the background, the picture of Newton to remind us that the greatest of scientific generalizations was now, after more than 200 years, to receive its first modification. So you can imagine the kind of atmosphere around it. And the next day, the London Times reported, revolution in science, Newton's ideas overthrown. 3 days later in the New York Times, lights all askew in the heavens. Man of science, notice only man of science, more or less agog, not completely agog, just more or less over results. So you get the sense of the feverish thing. But this catapulted Einstein into international superstardom, science superstardom. There's a ticker tape parade in New York, chatting up the film star Charlie Chaplin in Hollywood, with the Hopi Indians in Arizona, and here interacting with the press.
The ticker tape parade is for Einstein?
Yeah.
So he went in this
He visited
vehicle.
New York, and there was a big parade. I mean,
Oh,
this was he was like an overnight international celebrity.
okay.
Now, I've talked about this US skepticism. This was dampened somewhat when in 1922, during an eclipse, Campbell and Trumpler found a result that was in agreement with general relativity. So this damped that kind of criticism to some degree. On the other hand, especially in Germany, there was a backlash. The growth of anti-relativity campaigns headed up by people like Philippe Bernard, a Nobel Prize winner for his work on cathode rays in 1905, but who was an adherent to this new nascent Nazi ideology, wrote pamphlets and papers criticizing relativity as Jewish science, not proper science for people to study. Now, in this fairy tale history, there's another important episode that doesn't get much play. That is another aspect of this decline, and that's the gravitational redshift effect. This was a result of what Einstein later called his happiest thought, the idea that gravity in an accelerated elevator in an empty space, what you feel in an accelerated elevator, is the same as what you feel in an elevator at rest on the Earth, an equivalence between acceleration and gravity. Of course, we've made these ideas much more sophisticated in the present time, but for him, this was his so-called equivalence principle. But he then realized in an accelerated laboratory, a ray of light emitted from the roof would be blue shifted by the time it hit the floor, because the floor is now moving out faster, and you get an effective Doppler shift. So the same thing should happen in a gravitational field, a gravitational redshift if the light's climbing up, or blue shift if it's going down. And this was, he thought, was his most crucial test, not the deflection of light and not Mercury's perihelion, because this really was the foundation that ultimately led him to general relativity, to the idea that space-time must be curved. And so it was natural to set out to try to measure this effect by looking at the shift of spectral lines from the sun. And so, for example, the great spectroscopist Charles St. John and others at the Kodaikanal Observatory in India and many others tried the experiment, tried to measure the shift, and found no shift in the noise. I mean, they could not detect a solar redshift test. And some historians think this might have hurt Einstein's chances for the 1918 Nobel Prize. But as we know, the Nobel Committee then and today insist on some kind of experimental foundation for any kind of theoretical work. And this simply was not sufficient. And indeed, he got it for the photoelectric effect, not for general relativity, because that was solidly grounded. That theory was solidly in agreement with experiment. But another episode brings our friend Eddington back, and that was to try to measure this frequency shift in another place, namely using white dwarfs. By 1925, white dwarfs had been well studied. There were many of them. They understood their properties, stars comparable to the mass of the sun, but 100 to 1,000 times more compact. And so the redshift of light from their surfaces should be 100 to 1,000 times bigger than from the surface of the sun. And a leading candidate was Sirius B, the companion to the dog star, the brightest star in the night sky. It was a known white dwarf. So Adams, a spectroscopist at the Mount Wilson Observatory, took charge of measuring the spectral shifts from Sirius B. And Eddington worked out a theory of the white dwarf because although its mass was known because of its orbital motion, you had to have a theory you had to have the mass radius relation for the white dwarf to predict the radius, because that's what governs the shift of the spectral lines. It's a surface gravitational potential. And once again, in the referee journal, the New York Times, 1925, new test supports Einstein's theory. So apparently another triumph for Einstein. But very soon, within about a year, it all began to fall apart. Astronomers criticized Adams' measurements. They said the spectra were extremely complex, difficult to interpret, and they were likely contaminated by scattered light from the much brighter Sirius A. The red giant is very bright. And already in 1926, people like Ralph Fowler at Cambridge were realizing that white dwarfs were not some extreme low mass star at the end of the main sequence covered by the conventional equation of state, but rather white dwarfs, because of their high density, were probably governed by this newfangled thing that's just come along called quantum mechanics. And this is long before Chandrasekhar. The idea of degenerate matter was already taking hold, and Fowler criticized Eddington's calculations as simply not right, because these white dwarfs are not polydromes in the conventional sense. And so by 1950, and so the whole thing fell apart. And by 1950, Einstein had to admit that this test, for him, the most crucial test, had not yet been done.
Why was it the most crucial test?
I'm sorry?
Why did he think it was the most crucial?
Because it really was the foundation for the idea that space-time was curved. The other things are predictions from the specific field equations, but this really led him to abandoning flat space-time and really taking on curved space-time. So he thought if that failed, all else failed. And so far, it had not succeeded. Now, just one side remark about this. The experiment couldn't be done for another 50 years because you had to wait for the orbital motion of the two stars to bring them far enough apart that you could make clean measurements of the spectrum. This was done in 1971 by Jesse Greenstein at Caltech using better spectroscopy, the Mount Palomar telescope, and the latest and greatest white dwarf models, which were all in hand then. And they found complete agreement with general relativity. Nice test. However, what they found was that Adams' spectra were off by a factor of 4, and Eddington's radii were off by the same factor of 4. So Eddington and Adams agreed with each other, but not with nature. By the factor. And again, some historians of science had a field day with this idea, but again, most reasonable observers feel they did the best job they could, and the fact they agreed was, luck, good, bad, or indifferent, but just chance.
He gave them the benefit of the doubt.
Wasn't that due,
So, yeah.
was that due that because of the Hubble constant that they used at the time?
No, not the Sirius is right in our galaxy. There's no Hubble
Oh, yeah.
constant issue.
Yeah,
So it's a very close star. It was just, a complex problem, and sometimes but it was just weird that they both had the same, off by the same factor. So John Eisenstadt, a historian of general relativity, has called this period approaching the 1950s the low watermark for general relativity. It was considered to be the backwaters of physics and astronomy. And I'll cite to give two little anecdotes to illustrate the attitude during this period. In 1962, a young man just receiving his bachelor's degree from Caltech was on his way to Princeton to do graduate study. This young man was told by a very famous Caltech astronomer, when you get to Princeton, whatever you do, don't study general relativity because it will never, ever have anything to do with real physics and astronomy. Luckily for me and many others, that young man, whose name was Kip Thorne, ignored that advice and fell under the spell of Johnny Wheeler, and the rest is history. Also, at that very same year, by that time, the small GR community had started organizing international conferences. And that year, there was a conference retrospectively called GR3 in Jablana, Warsaw. And Feynman went to that conference and wrote back to his wife during the conference, because there are no experiments, this field is not an active one. So few of the best men are doing work in it. The result is that there are a host of dopes here, and it's not good for my blood pressure. So a common saying of this period was that general relativity is a theorist's paradise and an experimentalist's hell. So this gives you a sense of where the field sat at that point. But during the 1960s, it all began to change. There were many factors, but an important one simply was new discoveries in astronomy. Quasars, background radiation, pulsars, and by 1971, given the first black hole candidate from X-ray astronomy. And this really it began the process of a revival of general relativity. And one event, I want to just describe one event in this revival. The problem of the quasars was a very important one, because once these large redshifts were detected in early 1963, it was clear that the amount of energy they were emitting could not be explained by any normal nuclear or atomic process. It had to be something much more exotic. And so three relativists at the University of Texas at Dallas decided to organize a meeting. There were Ivor Robinson, Engelbert Schucking, and Alfred Schild, a meeting bringing together astronomers and astrophysicists with GR people to see if they could learn to talk to each other and try to solve the problem of the quasars. So they called this meeting, this was later called the first Texas Symposium on Relativistic Astrophysics. Meeting was called for 16 December 1963. Now, if you remember, this was just a few weeks after the assassination of President Kennedy in that city. So you can imagine the atmosphere just surrounding the whole event. In fact, the conference was opened, the attendees were greeted by Texas Governor John Connolly, who still had a sling on his arm because he had been hit by one of the bullets that were directed at President Kennedy. There were 240 astronomers in attendance and 60 relativists. I've looked at the list of attendees, and I'm old enough to recognize almost all the names. And I can tell you that the 60 relativists comprised essentially all of the world's relativists at that time, except for the ones in the USSR and behind the Iron Curtain. This, of course, was the heart of the Cold War. And even at this particular time, people feared we were even at war with the Russians after the assassination. So those scientists could never have come to this meeting in the first place, but anybody outside the Iron Curtain countries, 60, that's everybody in the field. And the big topic, of course, was explaining the quasars. So, for example, Willie Fowler from Caltech and Fred Hoyle from Cambridge came with their collaborators to talk about the gravitational collapse of supermassive stars, million solar mass stars that would collapse, and that would release a huge amount of energy, and that could then be enough to fuel the quasars. Tommy Gold came from Cornell to talk about, again, very massive relativistic star clusters that would collapse and release all that gravitational energy to produce the quasars. Johnny Wheeler, with his group, including a young first-year graduate student, Kip Thorne, talked about the collapse of compact objects. They were thinking about neutron stars, which are not really candidates for this, for quasars, but they were talking about how you could analyze these complex relativistic systems using the full machinery of pure general relativity. You could work out this kind of stuff using real, complete general relativity. But of course, it was all about the collapse. nobody at that time, and I've surveyed the papers, talked about the actual final thing, the black hole, as being the central engine of the power of the quasars. It was the process of the collapse. That's all they could conceive of. Although there was some understanding of black holes by this time, at least amongst more mathematically minded relativists, no one really could conceive of the black hole as a real object that could somehow influence its surroundings in a way that could produce quasars. That's, of course, that's today our accepted picture.
Were they studying also axisymmetric collapse, like with rotation?
This was all spherical because the computers weren't capable of doing anything beyond spherical symmetry, those at that point. There was even a paper at this meeting by a young mathematician from New Zealand, who was then at the University of Texas at Austin, who gave a paper, a very mathematical paper filled with killing vectors and hyperorthogonal vectors. And his title was Gravitational Collapse and Rotation, kind of an update on a paper he had published in Phys Rev Letters a few months before. Left the astronomers scratching their heads. They had no idea what this young man was talking about. They're completely befuddled. But those of people who were at the meeting, for example, my friend Bob Wagoner was there, vividly remember the relativist Achilles Papapetro standing up and turning to the audience and saying, admonishing the audience, I think we should pay very close attention to what this young man has done, because I think it could be very important. Now, not everybody at this conference felt the love. Phil Morrison, the astrophysicist, said he was interested in this idea of bringing these people together, but sort of not really persuaded that it would all amount to much. And the relativist Peter Bergman, he says said he was not very optimistic that this joining together would really go anywhere interesting. But it was Tommy Gold from Cornell who had the last laugh. At his banquet speech, he said, it was, I believe, chiefly Fred Hoyle's genius, which produced the extremely attractive idea that the relativists, with their sophisticated work, were not only magnificent cultural ornaments, but might actually be useful to science. Everyone is pleased. The relativists who feel they are being appreciated, who are suddenly experts in a field they hardly knew existed, the astrophysicists for having enlarged their domain, their empire, by the annexation of another subject, general relativity. It's all very pleasing. So let us all hope that it is right. What a shame it would be if we had to go and dismiss all the relativists. But this really was part of this nascent birthing of a renaissance for general relativity. And during the next decade of the 60s, it began to grow and grow. And I happened to be in the right place at the right time in the spring of 1969 at Caltech. This is the end of my first year at Caltech. And I managed to catch this relativistic wave. I never surfed, so I could never manage it. I body surfed, but so that's not me. Okay. Anyway, this is Caltech in the olden days. This is Bridge, where the relativity group was. And this was Kip's group at that time. Bill Burke, Richard Price, some of you know, who's now at MIT. Jim Mipser, John Dykla, Bernie Schutz, now a major figure in gravitational waves. Lisa, Wei-Tong Ni. They were working on the standard topics that you would expect, given Kip's interest in this growing field. Perturbations of black holes and the radiation they would emit, relativistic star clusters and their structure and stability, gravitational waves, structure of relativistic stars, and so on. So the whole group is involved in a lot of these topics. Now, I had come from Canada to go to Caltech, but within a year, I had completely adopted the Southern California lifestyle. But a big event occurred that very June that changed my career substantially. In June 1969 PRL and also in the New York Times, Joe Weber of the University of Maryland announced that he had detected gravitational waves. He had built gravitational wave detectors on solid cylinders of aluminum, put piezoelectric crystals around the middle so that as the aluminum stretched and distended from a passing gravitational waves, the stress on these crystals would generate an electric current and produce a strip chart. What's a strip chart? It's like what you see in movies about lie detector tests, a thing that goes like this, that records the oscillations of the bar, mostly from thermal noise and environmental noise, but he was looking for signals. He had a bar in Maryland at the University of Maryland and another bar at Argonne National Lab outside Chicago. The principle of simultaneous detection is one that he developed and now is part and parcel of all the modern day interferometers. But he was detecting events at several per week, sometimes several per day. And the strength of the signals that he detected was completely unbelievable compared to what you could understand from astrophysical sources. In today's language, we talk about LIGO measuring dimensional strains of 10 to the minus 22. He was probably measuring strains of 10 to the minus 17, maybe 10 to the minus 18, 100,000 times larger. No one could possibly explain this problem. And so a lot of students were trying to work on ways, things that might be an explanation. But Kip realized that all our calculations of gravitational wave energy fluxes and things come from general relativity. And so he worried that maybe general relativity is wrong. And he pointed to me. I think I was hiding in the back of the room behind Richard Price. He pointed to me and said, Cliff, your assignment is this summer, find out how right or wrong general relativity might be. So this is my starting graduate project. To read the literature and find out what the status was. And here's what I found. Things were not in great shape for general relativity in 1969. While it was true, for example, the Yotbush experiment, comparing the acceleration of bodies of different materials, that had been improved by Dickey at Princeton to a part in 10 to the 11th. That was very nice. The gravitational redshift had been measured for the first time, not using astronomy, but in the laboratory using gamma rays from radioactive iron, to first 10%, then 1% by Pound and Repka and Snyder. Finally, the solar redshift was measured by a student of Dickey's to about 5%. Mercury's perihelion advance, big test of general relativity, was still only known to about 20%. Not very good. And the diffraction of light was known from, say, from the most recent eclipse measurement in 1952, was not known any better than in Eddington's day, still about 10%. Meanwhile, of course, Dickey and his graduate student Carl Brands had invented a theory of gravity, now part of a class of what are called scalar tensor theories, that satisfied all existing tests to that date with a coupling constant omega of 7. So it was a completely viable competitor to general relativity. But in my reading, I also discovered that help might be on the way. For example, this newly invented technique of radar ranging, bouncing a radar signal off the surface of planets, promised to improve the accuracy of our knowledge of the planetary orbits and might help out with Mercury. This was discovered or developed in the early 1960s. And one of the pioneers of radar ranging, Erwin Shapiro, whom many of you know, discovered what he called the fourth test of general relativity. This is a theoretical discovery, this added delay in the propagation of a signal as it passes by a massive body like the sun. A few years later, Shapiro also noted that you could measure the deflection of light using radio waves. They deflect exactly the same as optical light, but you don't need a solar eclipse. You can do it in broad daylight, and you can use these quasars as your very point-like bright sources for waves. So he proposed using radio interferometry to do bending measurements. And meanwhile, NASA, in the middle of developing the Apollo program, considered putting laser retroreflectors, special reflectors that would reflect the laser beam exactly back in the direction from which it came on the moon as part of the Apollo project. The idea really pushed by Dickey to measure long-term changes in big G, Newton's constant. But we'll see in a moment, it turned out to have a much more important consequence. Kip sent me up to JPL, Jet Propulsion Laboratory, to talk to the people there. Shapiro had actually measured his time delay effect in 1968 using signals bounced off Mercury and Venus. But JPL was managing the Mariner 6 and 7 missions to Mars. And after they had encountered Mars, were set to go off behind the sun on the far side. And they were planning a measurement of the Shapiro delay as well. And I went up to talk to them about what kind of accuracy they expected to achieve. But my big discovery that summer was 3 remarkable papers by a man named Kenneth Nordtvedt Jr. at Montana State University. Ken had taken the post-Newtonian metric of general relativity. These include the first post-Newtonian corrections beyond Newtonian theory for a weak field slow motion system, stuck a parameter in front of each term in that metric, and then calculated various observable effects. In the second paper, he calculated, and the system we looked at was a system of what relativists call dust, just point particles all moving around in their mutual gravitational fields. So in the second paper, he calculated the acceleration of a cloud of such dust particles held together by their own self-gravitational interaction in the field of some, say, distant body. And he discovered that the acceleration was not the same as that of a single individual test particle. It was different by the amount of gravitational binding energy that body contained. Unless you were in general relativity. In general relativity, there was a cancellation and the effect for everything was zero and a bound body would follow the same as a test body. But in other theories, in some generic theory, it would not be the same. And in particular, in Dickey's scalar tensor theory, there would be a violation of what he called the strong equivalent, what we call the strong equivalence principle. Today, we call this difference in acceleration that can occur in order to that effect. And in the third paper, he proposed that you could test this effect by looking for this differential acceleration in the Earth-Moon system in the field of the sun using the lunar laser ranging that was being proposed for the Apollo mission.
Would this also not lead to a violation of the weak equivalence principle?
No, the weak equivalence principle just really refers to non-self-gravitating bodies like laboratory scale bodies. I mean, yeah. So during Kip's course that prior year, I had done a term paper studying Chandrasekhar's post-Newtonian version of hydrodynamics, post-Newtonian version of hydrodynamics, where you talk about real matter, not dust particles, but bodies made of real fluids with pressure, internal energy of various sorts, and so on. And I realized that I could generalize Ken's point mass description by using a perfect fluid description, which would be much more realistic when you want to talk about real bodies. So I developed my own parameterization, and with Kip, we call this the parameterized post-Newtonian or PPN formulas. And then later in 1971, at a workshop organized by Nordvet and Montana State in Bozeman, Ken and I combined our two approaches, normalized everything, got the same conventions, and used the same parameters. And so we produced kind of a canonical PPN formalism that in subsequent years became the workhorse for testing GR in the weak field limit. So there are a set of parameters that describe various aspects of physics, aspects of gravity. Gamma is a very important one, describes space curvature. These two are one in general relativity. Some parameters describe whether there's an apparent violation of Lorentz invariance in gravity. Again, zero in general relativity, but could be non-zero in certain other alternative theories. So this became something that was widely used. And during that decade of the 70s, it was almost a golden age for testing general relativity, at least in the weak field limit. So the Shapiro delay was measured by many experiments. Here I've quoted the dates of the papers, not of the actual missions. Mariner 6 and 7, Mariner 9, culminating in Viking, measuring this gamma to 0.1%. The gravitational redshift effect was measured by setting clocks around the world on aircraft, but the best measurement was, until recently, was a project called Gravity Probe A, putting a hydrogen maser on a rocket on a suborbital flight. There's Bob Bessot, one of the pioneers of hydrogen maser clocks at MIT and later here at Harvard, and his colleague Marty Levine holding one of their hydrogen maser clocks. And that verified the redshift to about 0.02%. Mercury's perihelion, finally using the improvements brought about by ranging to the planets, was now finally known, compiling a bunch of data to 0.5%. And with laser ranging, people looked for this Nordvet effect and it found zero. In general relativity, it should be zero. And it was down to the level of 1976 of 0.01 times whatever the relevant parameter is. And of course, in recent years, these have been improved in some cases by 2 to 3, 4 orders of magnitude using better experiments, improved data, all kinds of exotic systems. But the final kind of capstone event of this particular decade of the 1970s began in 1974. I had arrived at Stanford as a young green assistant professor to work mainly with Bob Wegener, one of the pioneers of Big Bang nucleosynthesis, but had lately, again, spurred on by Weber's claims, had lately become very interested in gravitational radiation. So it was a great thrill for me to go to be able to work with Bob. and during the 7 years I was a stamper, I really enjoyed working with one of the most nicest and most enthusiastic scientists I know. So in September 1974, I was sitting in my office, I just finished getting settled in. Bob bursts into my office holding an IAU telegram. Now, when I say this, mention this to young people, they often say, "What's a telegram?" Well, an IAU telegram is a very special telegram that used to be sent out by the International Astronomical Unit to all the observatories and universities around the world, announcing new discoveries in astronomy. The service still exists, but of course it's now done by email and on the web. So Bob burst in and said, waving this IAU telegram that he just got, and he said, "They've just discovered a binary pulsar. Whatever you're working on, drop it. We've all got to work on this new thing." So Bob wrote a paper on the gravitational wave emission from this new system and what it would imply for the damping of the orbit, the shrinkage of the orbit, and predicted that at current measurement accuracies in 15 years, they could measure this damping effect. And I wrote a paper on the implications of when they measured the pericenter advance of the orbit, what that would imply for alternative theories of gravity. And of course, we all know this is the famous Hulse-Taylor binary pulsar discovered at our dearly departed friend, the Arecibo Radio Telescope. Our graduate student Russell Hulse, working for Joe Taylor then at the University of Massachusetts, found a pulsar whose period was going crazy, but once he saw it decrease and then rapidly turn around and increase, he realized he was seeing orbital motion, not a crazy pulsar, orbital motion of one pulsar around another star. And this, of course, was a great discovery and led to the Nobel Prize. And of course, Taylor beat Wagner's prediction for measuring it. He actually measured it within 4 years, not 15, largely because they improved the measurement accuracy. Various de-dispersing techniques at Arecibo, lots of tricks that so they measured the rate of change of the orbital period and announced it in December 1978 at the 9th Texas Symposium in Munich. Now, I love this. I think it's one of the most fantastic curves in astronomy. So this plots the time of pericenter passage, which if the orbital period is changing at some rate, should be a quadratically decreasing curve. And these are the data points from 1974 all the way to 2005. It keeps going. The curve is not a fit to those points. This is a general relativistic prediction using this conventional quadrupole formula, using the known two masses and all the other orbital parameters, which you also get separately from data on the binary system. And the little error bars here are multiplied by a factor of like 400, just so you can see them. So a complete agreement between general relativity, and these days one quotes it at actually of 0.1% between theory and experiment. But what Taylor reported at the Texas Symposium was this piece of the data, just 4 years worth, but it was enough for him to report that the period was changing at an amount that agreed with general relativity. And so, of course, in 1993, they were awarded the Nobel Prize in Physics, one of the first time the prize had ever been awarded for work directly related to general relativity and Einstein's theory. This, of course, was great for us in the field, great because Joe is such a great person. He's a real mensch. We all love Joe Taylor. But then a few days later, I got a very fat envelope from Stockholm from the Nobel Foundation inviting me to attend the festivities. This was an invitation from the foundation, not from Taylor, from the Nobel people, and to come, all expenses paid, stay at the Grand Hotel, tickets to all the events. Now, it did come with one caveat. They would fly me business class to Stockholm, but if I wanted, I could bring my wife, but we'd then have to fly economy class. So I pondered that for a while. But the fact that I'm here giving this talk tells you I made the right decision. And just to prove that I do know how to dress up properly once in a while, white tie tails at the festivities. So it was actually a fantastic experience. I mean, it was great. So this really was the capstone of this remarkable decade of testing general relativity. And from then on, it was kind of general relativity was becoming part of the mainstream of physics and just grew and grew and grew. But I want to just illustrate an important factor or aspect of science that, and again, based on my own experiences, And that's the synergy between theory and experiment. And this really has to do with the binary pulsar. Soon after the discovery of the binary pulsar, an important paper was published in Phys Rev Letters by Jürgen Ehlers and his collaborators that criticized the foundations of the equations of motion or radiation reaction in general relativity. Basically, they said that the quadrupole formula that we use to calculate all of these things, is things like the binary pulsar, has actually no basis in general relativity. It cannot be justified as an actual prediction of the theory because all calculations done heretofore were deeply flawed. They pointed out, for example, that a lot of people just use linearized theory, as Einstein did in 1918. You can't do that. You have to use the nonlinear aspects of GR to get the quadrupole to calculate gravitational waves. They said everybody tends to treat their bodies as point masses, and they just put delta functions in. You can't do that because the delta functions don't exist in general relativity. If you take an object and try to shrink it holding its mass constant, you get a black hole. And so you have to treat it as a black hole. And of course, that's a very complicated thing to do, and no one had done it. They pointed out that these are slow motion systems, so you treat things in a multipole expansion, just as you do in electrodynamics. In electrodynamics, you can do it because the charges are confined to where to fixed places. They have compact support in mathematics language. So you can calculate these multiples. But in general relativity, the gravitational fields produced by these particles extend all through to infinity, and gravity carries mass and energy itself. So your multiple moments have to include the contributions of the gravitational energy that goes to infinity, and it doesn't fall off fast enough to guarantee that you'll get multiple moments that will all converge. So they've said that these problems are filled with divergences. So how can you even believe the result of these calculations?
Is this after the Dixon's papers on multiple expansion? Or
Yeah, I mean, they knew all of this.
they knew all
These are all very formal and yes. And finally, they said that, for example, what you calculate, even if you believed your quadrupole formula, you calculate the energy flux in infinity. But you then assume energy balance, that the orbit loses energy at the same rate, and that's what causes the orbit to inspiral. There's no proof in general relativity that energy balance is correct. It makes sense, you might believe it, but there's actually no hard proof that it's valid. This paper really annoyed us in the field. We got very angry. We got angry in the same sense that when your mother tells you to eat your vegetables, you get really angry. You don't want your mother telling you to eat your vegetables, even though you know she's right. Vegetables are good for you. Just don't tell me to eat my vegetables. So in fact, they were completely correct. And for instance, at the same time, Bob Wagner and I were calculating the first post-Newtonian corrections to the quadrupole formula. So this had never been done before, based on work Wagner had done with his student Ruben Epstein. And I can assure you, in our calculation, we did much sweeping of divergences onto the right. We argued that they wouldn't matter. We thought we had cogent arguments, but nevertheless, there were integrals that blew up. But we said, well, you then eventually have to take a time derivative for the integral, and a time derivative of infinity is clearly zero. I mean, that's the level where we were working. And that's really, the Ehlers paper did have the effect, and of course, many of us, to go back to the basics and really re-examine how all these kinds of perturbative calculations were done in general relativity for the equations of motion, the radiation flux, and the back reaction on the system of the emitted radiation. Now, the fact that the Taylor's announcement that measurements of the binary pulsar orbit actually did agree with the quadrupole formula was very nice, but not completely comforting. Just remember, Eddington and Adams' theory agreed with experiment, but not with nature. So we were forced by this observation to take these ideas seriously. Furthermore, by the 1990s, we've worked on a lot of these problems for about a decade in the context of binary pulsar motion. But by the 1990s, we were being told that that wasn't even enough. Not only did we have to figure out how to do these things, answering all these criticisms, we had to even go higher than the 1 p.n. order that Wagner and I had done, because in order to satisfy the needs of interferometric gravitational wave detectors. They were telling us we might need predictions for the gravitational waveforms accurate to 2 p.n. order, maybe 3 p.n. order. In fact, today we're at 4.5 p.n. order, post-Newtonian order, in these gravitation waveform predictions. So we were driven to develop a lot of this theory by these requirements for gravitational wave detectors. And many different formalisms and methods were developed. In France, the post-Minkowski framework, this Dyer framework from my group at Washington University. Even the particle physicists began to get involved using a vector field theory to start calculating these kinds of perturbative results in gravitational wave motion and radiation and so on. We even had to start thinking about alternative theories of gravity because that became a key goal of these detectors. Well, in 1999, at a seminar or a conference in Kyoto, I gave a talk reviewing this kind of decade of progress, developing all these methods in response to Ehlers et al. And Jürgen was at the conference too, giving a talk on gravitational lensing, as I recall. And somebody after my talk turned to Jürgen and said, "Well, Jürgen, are you now happy with all these new results?" And Jürgen being Jürgen said, he was, after some pressing, he was willing to admit that he was happier than he was before, but not completely happy. And Jürgen was one of the great mathematicians of the era. And so I viewed that, the fact that he was happier, as a good housekeeping seal of approval. Right, this energy, the fact that experiment now pushes theory to do certain things is something that was lacking in the early days. And we now really have a healthy interaction between theorists and experimentalists in this game. And I think that's what has helped make it such an exciting field ever since the late 1970s. So I want to just again illustrate this change by reminding you that in GR3, Feynman complained that there were no experiments. Well, in fact, there was one talk on experiment given by Vitaly Ginzburg, as it turns out, at this conference, just one talk. But at GR22 in 2019 in Valencia, Spain, of the 18 plenary talks, 10 talks were on aspects of experiment and observation. There were 4 talks, of course, on all the various gravitational wave detectors, 2 talks on precision observational cosmology, a talk on looking at stars at the galactic center, orbiting Sagittarius A star, a talk on the earliest Event Horizon Telescope results. There was even a talk on something called analog gravity. This is efforts by people using exotic laboratory systems like Bose-Einstein condensates and exotic fluid systems to try to find evidence for Hawking radiation by producing sonic horizons. Turns out that Hawking radiation is not generic to black holes. It's generic to the idea of a horizon, an event horizon. Well, you can have sonic horizons where with sound waves you cannot go out from one place to another. Do these sonic horizons produce Hawking radiation? And the final talk, since this was the 20th anniversary of Eddington's famous measurement, the final talk given by me, as it happened, was on experimental tests of GR, also summarizing Eddington's famous result. So this illustrates, again, the change that occurred during these decades. So I think we can remember Tommy Gould's admonishment about dismissing the relativists. I think the relativists are here to stay. I don't think we necessarily still feel the love that was hoped for in 1963, but I don't think they're ready to get rid of us just yet. Thank you very much.
Right, thank you so much. Questions?
Yeah, I have a question. I was looking for a quote. There was an article a few years ago, and it was talking about stellar orbits and LIGO and EHD and all this breakthrough. And there's a quote from Bob Wald, which is, "I don't think we're going to learn anything more about general relativity or the theory of black holes from any of this." And it's there's kind of a tension, I think, these days between. I guess I'm just curious. What do you think this next series of experiments? Where do you think they're pushing theory, and where are you most excited to see progress?
Well, I mean, this whole idea of testing general relativity with things like black holes, event horizon imaging, and so on, it's sort of complicated in the sense that there isn't a stable of theories that you could write down and say, if we do this, this theory's dead. so on. I mean, the latest example was when they measured the speed of gravitational waves and found it equal to the speed. That turned out to kill a bunch of theories, but that was, in my view, a kind of rare example. So it is kind of hard, and since many alternative theories of gravity are invented these days to address issues in cosmology, dark energy, dark matter, not astrophysical scale issues, their general relativity seems to work fine. And so it's the kind of thing where would you say that trying to test general relativity around a black hole should be the main science driver for an expensive mission? I'm not sure I would say that. But if you have strong science drivers, and by the way, if you do this, you'll narrow the parameter space, that would be a great, supplementary reason to do it, but you have a different science driver for that mission. And it's just that there are no targets. Quantum gravity, well, the target is the Planck scale. We're never going to get there. Now, that's my opinion. Some people might disagree, but the simplest kind of quantum gravity, we're just never going to reach. Exotic kinds of gravity based on, say, dark energy or acceleration of the universe, maybe there's a place where you could go, but these things tend to be flexible and fungible, like Brans-Dicke's constant. And so it's hard to point to a target that you'll say. On the other hand, it's all science and it's good to learn more. It's a question of what weight you give to different things. So I think Bob is giving an extreme version. I agree with him in some respects, but I think I would be more nuanced in what I say.
Thank you for this amazing talk and this wonderful overview. There's one experiment that you didn't talk too much about in the 1970s, and I'm very curious in how you received Joe Weber's results in 1969 and how your thoughts on that developed in the 70s, together with the rest of the people around you.
Well, most of us, we were very disturbed about it because there was no ready explanation for it. And of course, I was a graduate student, so I completely buried myself. Gee, do graduate students do that, bury themselves in what they're doing and ignore what's going on around them? So I really had my own agenda to work on, but it was still an issue. But I remember in the 70s attending conferences. Within a year, other groups were building their own detectors, including at Stanford. Another reason why it was, for me, great to be there. Bill Fairbank's group was building cryogenic Weber type detectors, all in an effort to replicate or refute Weber's results. In the end, they all refuted them. No evidence for any gravitational waves was found. On the other hand, no one could point to any smoking gun to say, this is what Weber thought he saw. This is what he claimed, but we now know what it was. A lot of it was just poor understanding of statistics, which Weber really had a very rudimentary understanding. When you think of what we do today with Bayes statistics and Bayesian approaches, very fancy, very, very with a strong foundation. His was seat of the pants statistics, reading these strip chart recorders by eye, comparing the two strips. On the other hand, he could take two strips from the two detectors. And there's another principle that's used by LIGO. He would take the two strips and offset them by various amounts. So there can't be coincidences because you offset them by an hour. So any coincidences you see are just coincidental noise. So use that to establish his noise. LIGO now does the same thing. So a lot of the things he did established principles that were taken over by, of course, seismic isolation. That's a biggie that everyone must do. But then when the time delay was zero, the number of coincidences would jump dramatically. So, how do you explain that? Now, unconscious bias, was he seeing things? So nobody could say, this is what you did wrong, and if we correct this, it all goes away. At the end of the day, of course, once other experiments saw nothing, people saw no gain in trying to revisit it, so it died away. But Joe believed it till the end. He never gave up.
Did it damage the field according to you?
Not in my opinion. I mean, in some circles, it gave a bit of a bad reputation. But it spurred on a lot of theoretical work. So for example, just in Kipp's group, it was clear that perturbations of Schwarzschild black hole would not do anything. By then, Price and other people that could estimate the radiation wasn't enough. But what about the rotating black hole? Maybe because of this frame dragging, you could get what people then called synchrotron gravitational radiation. If the radiation were beamed, then you could get a big flux if you just happen to catch the beam, and maybe frame dragging would induce it. So he said students were looking at perturbations of the curve metric, and Colloquium, of course, had the famous breakthrough separating the equations that allowed people to do these calculations. They did it, and there was no synchrotron gravitational radiation. So it really spurred on, and of course, it spurred a lot of people to think about weak field gravitational radiation, especially after 1974. So a lot of theoretical work was done in response to Weber. And the second benefit, in my opinion, is that it brought people into gravitational physics from other fields, notably experimentalists, like Tony Tyson from Bell Labs, Bill Fairbank from low temperatures, Vladimir Baginsky in Moscow from measurement theory, David Douglas, a particle physicist at Rochester. They all built gravitational wave detectors. Ray Weiss started thinking about it too, and started thinking about his own kind of gravitational wave detector, but he was not a gravitational physicist. So it brought people into the field, especially experimentalists, that I think changed the field in a positive direction.
There's two hands in the audience, but I also want to do the few questions.
Yeah, we have a couple of questions online. We will go first with Shep and then with Dennis.
Hi, can you guys hear me?
Yes.
Yeah, okay, great talk, Cliff. That was really fabulous. Sorry, I can't be there in person. The quick question I have is that when you mentioned the archival work that the US scientists had done on the earlier eclipses and their negative result, it made me think, have there been some other missed opportunities? I mean, after the Snyder-Oppenheimer paper in 39, there seems to be this long period between them then and the 1960s and 70s when things took off experimentally. Were there some other opportunities that in retrospect would have led to a faster acceleration of the whole field?
Well, I mean, the Oppenheimer-Snyder paper, I think, is an example that of a paper that this is the paper that Oppenheimer and Snyder did doing the gravitational collapse of a body to form a black hole. This was written in 1939, and if you read it today, it reads like a modern paper in GR. They worked out the fact of what the star would look like to an observer at infinity, that the luminosity would exponentially decrease. This is stuff in modern textbooks. They showed that an observer riding the surface of the star would not feel anything singular. In those days, it was called the Schwarzschild singularity, but in fact, nothing singular happened as the thing went in. So it had all the modern ingredients. But there was a great point in the Oppenheimer movie, if you saw it, that there's a scene where Oppenheimer is in a room with a bunch of colleagues, and somebody walks in. Oh, your paper with Harlan Snyder just got published, and Oppenheimer says, "Oh, where's Harlan? Well, let's bring him in." And then somebody else walks into the room and said, "Germany just invaded Poland." And I actually looked it up. The paper was published on September 1, 1939, the day of the invasion. So obviously, so that paper disappeared from history for a long time until the 60s, people rediscovered it. Yet it has all the modern ingredients of a beautiful, general relativistically based paper. It's amazing. But so that was a missed opportunity, but there are, I think, good reasons why it was missed.
And Dennis?
Yes, thank you. Hi, Cliff. I wondered if you could say a little bit more about the work together with Kip that led to the development of the PPN formalism and the role that Chandra's work played for that. So you commented on this. I just wondered if you could say a bit more.
Well, I mean, as I said, I had studied Chandra's papers as part of this term project that I was supposed to do. We all had to do a term project. And basically, in my project, I showed that you could take this fluid description and make the bodies small compared to their separations, and then work out basically the effective point mass equations of motion. I therefore re-derived the famous Einstein-Infeld-Hoffman results of 1939, great achievement, right? But from a completely different point of view from theirs. And so, and I think that paper must have impressed Kip. But then, since I knew this, it was just clear that we could do what Nordtvedt had done, but in this fluid picture, there are two additional parameters that we needed because now we had pressure, and so maybe pressure could generate gravity in some weird way, and internal energy. So we had two more parameters than he did because we had a different model for matter. And then in my PhD work, I showed, for example, that in certain theories of gravity, bodies moving relative to the mean mass frame of the universe would have different gravitational behaviors than bodies at rest, a kind of violation of Lorentz invariance if certain of these parameters were non-zero. There were 0 in GR, so nothing like that occurs. And I actually remember telling this to Kip, and he said, I don't believe it. He was so embedded in general relativity and everything being Lorentz invariant, he said, how could that be? Eventually, I convinced him that in these other theories of gravity, which have weird, like vector fields that can, if they're attached to the cosmic distribution of matter, can give a preferred frame, like the frame in which the field is purely time-like, that such a thing could occur in the right kind of alternative. So he finally believed it. So I worked out a bunch of things, but then at this conference that Nordvet organized, it turns out that also at this conference was a student of Kip's named Shandor Kovacs, who later became a noted cardiologist at the Washington University Medical School, who confronted Ken and me and said, if you two guys don't make your formalisms agree, I used plus, minus, 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 he used minus, plus, 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 he used point masses, I used fluids, we had different parameters, different indices. He said, I'm going to lock you in a room and not let you out until you compromise and come up with a canonical formalism that people will actually use. And so he nagged us so much that that's what we did.
Brilliant. Thank you.
Priya, so just a quick question. So do you think that the Texas Symposium, the fact that there was a forum now that brought together astronomers, astrophysicists, played a critical role in the development of generating more interest and building this sort of new community?
Yeah, I think it's especially in the early days because of Weber. I mean, there were always talks on either what Weber had done or what somebody else was doing on gravitational waves in the early symposia. I think I probably went to 3 of the early ones between, well, I wasn't 1963. I was still in the, I think I was in high school still. But in the 70s, I went to a few. So there were talks on that. There were some talks on GR. Over time, in the later years, GR kind of fell away or became so embedded in what everyone was doing that general relativity kind of lost its aspect as an ingredient of the meeting. I think it just got absorbed, as some people said. We really got absorbed by the astrophysicists because a lot of it just was about black holes and gravitational waves, modern gravitational waves. So, but I think it played a role in some sense forcing the astrophysicists to hear some GR talks as part of those early meetings and get them into the idea that this is all part of the story.
No, wonderful talk. Thank you. I was thinking a lot about recently about the role of testing GR and to what extent are we testing GR, and have we come to a point where we're using GR rather than testing it? And it, you know, from your talk and writing, I imagine this is sort of a sympathetic idea, but I think about Maxwell, for example. Maxwell was clearly being tested by Hertz, but by 1903, when Marconi is having Theodore Roosevelt address the King of England across the ocean, he's not testing Maxwell, he's using Maxwell, right? And you know, as I heard your talk, it seems like there's a transition. I don't know exactly where I would put it when saying we're testing general relativity is yielding to something else, an exploration of the phenomena of general relativity, a use of general relativity to explain and be applied to other areas. Tremendously exciting, but in a sense, the idea is if we're going to thumbs up or thumbs down general relativity no longer seems like the main event. The main event is understanding space-time or understanding black holes or understand. I mean, where do you? I mean, I think if you see something like that too, but where do you see that?
So I think there was some of that beginning with the binary pulsar, in that I mean, think about the solar system tests. It's weak field. We know the bodies. It's clean, right?
Mm-hmm.
The solar system moves in a clean fashion to some degree, and then we can look for relativistic effects cleanly superposed on Newtonian. So the binary pulsar, for example, and I've I do this both ways, testing GR and whatever, but I also talk about the binary pulsar as the first time, literally the first time, when general relativity was used to make an astrophysical measurement. Because once you measure the mass function and the pericenter advance, you get the two masses separately. That had never been done before, and you get them accurately. No one had ever measured a neutron star mass to a percent until then. So here, so I used to be proud of the fact that general relativity was a tool to make astrophysical measurements. On the other hand, you can still test alternative theories, but you have to calculate their predictions. And it's in these realms, gravitational waves, compact objects, the kind of PPN formalism that worked in the solar system just isn't available, because these theories can be so different in these dynamical strong field areas. It's very difficult to think of how you even parameterize them. So you can measure a number and say, this list of theories agrees, this list doesn't. So in some sense, you have to go theory by theory and see what it predicts. And so that loses this kind of flavor of just purely testing GR. But in my view, it sort of started with the binary pulsar, because even the existence of the neutron star introduced strong field of gravity that you had to somehow incorporate into the discussion. Say nothing of gravitational waves. I mean, there are theories of gravity that predict anti-damping, negative energy flux. Now, quantum physicists might object, but it's a classical theory, it predicts, and so taking it on face value, then you could rule out that theory. But then you have to go to the next theory to see what it is.
Big one.
So quick questions, but my answers tend to be long.
So there was a long period of time when general relativists were arguing whether gravitational waves are real, right? Or it's just some coordinate confusion. Had that ended before the Hulse-Taylor discovery, or was that the time when people said, look, the thing is real, this guy is radiating it?
It pretty much ended by the late 50s.
50s, okay.
Yeah, because some people describe it to Feynman's sticky bead argument.
Yes, that I've heard, yeah.
North Carolina meeting. But it was really some work by Felix Pirani and Bondi and his group in England, who showed in very mathematical terms, rigorous terms, that gravitational waves carry energy flux to infinity. They couldn't say too much about what the reaction of the source would be. That would be too complicated. But this was a real phenomenon. And you work out the guiding thing is the Riemann tensor, the curvature tensor. And it produces real physical effects. And Pirani worked this out in great detail. So I think by the early 60s, it was pretty clear that, pretty accepted that they were real.
Okay.
But there was a second thread. Certainly they were real if you had a dumbbell rotating around, as Einstein did. But what about two bodies orbiting themselves? Now, in some sense, each body suffers zero acceleration in the four-dimensional terms. They're moving, each is moving on a geodesic. So its four acceleration vanishes. So that must mean there's no gravitational radiation. For example, Peter Habash, one of Ehler's collaborators in this famous paper, firmly believed that dumbbells would emit gravitational waves, but binary systems would not, because each particle was moving on a geodesic and was therefore unaccelerated in some formal sense. But that was a very, very minority position.
But was that part of this Jürgen Ehler's 1976 argument?
I mean, yeah, it was the fact that people had not really shown that with these equations of motion, that the underlying theory was so flawed that you couldn't automatically believe it. And you could even believe something as extreme as Habash. Now, I don't think Ehler has agreed with what Habash claimed. I'm sure Jürgen believed that binary systems emit gravitational radiation, but that we just needed a better way to prove it theoretically.
Okay.
Okay, thank you, everybody, and join me in English. I believe there's now